Okay, hi guys. So in this lecture, we'll be seeing deactivating groups or meta directing groups. In the previous lecture, we saw activating groups or ortho and para directing groups, and um, this is the direction with respect to the coming electrophile. Okay, so let's get started. So we have now deactivating or meta directing groups. Okay, so these are strong meta directing groups, and these are NO2 N plus H3 SO3H and nitrile group. These are moderately meta directing groups, and these are this one carboxylic acid and acid halide. Okay, and these are weakly meta directing groups or weak deactivating groups. These are okay. Now let's see some examples. So this group was, as we discussed in the previous lecture, it was activating group. Okay, OH on a benzene ring or a phenol is an activating group, hence this would be a ortho para directing. Now let's see what actually happens, why it is ortho and para directing. Okay, so what actually happens is, if this bond actually breaks, so here we'll be getting a positive sign and electrophile attaches itself here, and we get OH here and two other bonds here. Okay, so if you see the total number of resonating structures in this case, it would be 4 resonating structures. How? You are sufficient enough or and capable enough to count how, right? One can be like this, second can be like this, third can be like this, and fourth can be the extended one. This one, then this one. So 4 resonating structures are there. And how many resonating structures are there for this case? So we have OH here, so this is only having 3 resonating structures and positive charge obviously here. Okay, so the one which would not be in the resonance is from the lone pair of this oxygen and from the lone pair of this oxygen. We won't be having any resonating structures. Okay, let's see what about the para group. When the electrophile actually attaches itself to the para position, what actually happens in this case is we'll get something like positive sign here. Again, this would be having 4 resonating structures. As the stability of carbocation is more in ortho and para positioned electrophile, hence it would be ortho and para directing to the with respect to the electrophile. Okay, now let us see second example wherein we have something like this or a nitro group. So what actually happens in this case is we have N plus here and negative charge here. What actually happens in this case is, let's actually draw the resonating structure when we actually attach electrophile towards it on the phenyl ring. So if we attach the electrophile on the ortho position, we have double bonds here and here and a positive charge here and NO2 group already attached here. Okay, so this would be highly unstable. Why? Already the nitrogen in the compound, the overall compound was positively charged, and on the top of it the neighboring carbon atom of the nitrogen atom is again positively charged. This will make the overall compound highly unstable. But on the other hand, if we have something like this, electrophile attaches itself to this position and we have something like this, this is relatively lesser unstable, or this is relatively, or better in better words, it is relatively more stable. Okay, so hence NO2 group would be meta directing. Let's look at third example where we have something like this group, NH2 group. we have something like this, and let's see it is orthodirecting or meta-directing. So if we actually attach the electrophile on the ortho position, we would have negative positive charge on this carbon atom, which is adjacent to the lone pair of nitrogen atom, and will have resonating structures as well. Hence this acts as a plus M group, hence this would be ortho para directing. Okay, let's see. In this case we have something like CH3 here. Okay, and obviously the phenyl ring, which makes it a toluene group. So let's see what happens if we have the electrophile attached in ortho position. We would have positive charge here and CH3 here, and in the other case, if we attach this electrophile on meta position related to the CH3 group, then we would have something like positive charge here, and we would have double bonds here and here. So here again you can see the number of resonating structures are the same in both the cases, but in this case we would have the additional effect of plus I attached close to the carbocation, hence this would be more stable. And same can I see the same for this meta group, meta attached electrophile? No, because it is relatively at a farther distance than CH3. Okay, so this would be ortho para directing as well. Okay, before seeing the next example, let us why did I see this? It is also a para directing group. It is ortho because the positive charge is nearer to the CH3 group, but why it is a better para directing as well? So all answers lie in the resonating structure or in the inductive effect. If let us see if it attaches itself, the electrophile attaches itself on the para position. Now what happens is we'll have positive charge here and two bonds here and here. Okay, again in this case, if you can compare the position of positively charged, it is nearer to the ortho position than para position and then meta position. Okay, in the meta position it would have the least stability, the overall compound or the carbocation, hence meta would be the least. Hence in generality we say that it is ortho and para direction, but if we have to choose one answer, then obviously it would be ortho directing because of the closeness of the plus I effect group nearer to the carbocation. Okay, let's jump to another example. Now we have something like this. We have SET here. Okay, so obviously it would be activating group and it would be ortho and para directing. Why? Just like oxygen, as sulfur also belongs to the same group, it would also donate its lone pair to rescue the positively charged carbocation, which can be formed here and here. Okay, positively charged would be formed not here. This is the place where electrophile will be attached. Positively charged would be formed here. Okay, hence this carbon and this carbon would be supported by the resonating structures of the lone pairs. From the lone pairs, conjugation with pi bonds, hence it is a ortho and para directing group. Okay, let's look at 6th example. Here we have something like SO double bond OT. So in this case this group acts as a minus M group. Okay, and this is then a deactivating group, and this is meta directing. Okay, because this carbon atom and this carbon atom would be having a partial positive charge because of the plus M effect of the phenyl group. Okay, hence it would be better that the incoming electrophile attaches on this carbon atom or the meta positions. Okay, let's look at another example. We have something like this group, N plus double bond N minus rather, So what happens in this case is, oh, let me first draw it, or rather it won't be having any charge because it would be having a lone pair. Okay, so it would be obviously delta minus will come on ortho and para positions, hence it would be activating with ortho and para positions. Okay, someone might come in and see that we can have something like this, means this can act as a plus m for this NO group, and we have something like this. So this can be my plus m also in that case. Okay, so for this compound it can be a deactivating group as well, with obviously meta directing, because it can take the electron or pi electrons away from itself and contribute to O minus. Okay, you can have something like that as well. So what will happen in that case? So the correct answer would be this compound and this compound. If you closely look, in both the compounds, oxygen atoms are double bonded with the sulfur and nitrogen atoms here and here. Although they are deactivating groups, it does not mean that every deactivating group would be meta directing. Okay, they are deactivating groups and they are in fact ortho and para directing. Okay, so how this mystery is solved, you can actually draw the intermediate structure and we can actually decide. So what decides the deactivating character? The deactivating character is just decided by the plus m, whether the plus m effect is on the phenyl ring or the minus m effect is on the phenyl ring. If there is a plus m effect, then the overall compound is a deactivating compound, but it would be a ortho and para directing. Why? Because of lone pairs available from the atom which is directly attached to the phenyl ring. In case if needed in the intermediate, still these are all the ortho and para positions are delta positive directions till the point that no electrophile is attacking it. But when the electrophile actually attacks it, what compound or what Wheeler intermediate or arena man we get to see in case of SO2H SOET is, we have something like, let's suppose electrophile attaches itself on the ortho or ortho position for this example. So what will S double bond OET do? That S has actually lone pairs, it will donate to stabilize the intermediate. Okay, but whenever the electrophile is not there, what will actually happen is simple, we'll have something like this, wherein the double bond would be actually in conjugation with the sulfur and the phenyl ring would act as plus m effect group. We'll have something like this and we would have an positive charge here. Okay, but as soon as the electrophile attaches, it will have ortho and para directing. The same can be seen for this compound as well. We had rather an O group here, and in normal case when the electrophile is not there, we definitely will have something resonating structures like this, in which NO group will actually take the electrons away from the benzene ring or phenyl ring, and the phenyl ring would act as a plus M group with this as the resonating structures. Okay, and resonating hybrid being something like delta negative, delta positive, delta positive, and delta positive. And in case of SO2H or SOET as well, we would have something like, in normal case, normal conditions, it would be O delta and O minus delta and SOET. Okay, but whenever the nucleophile comes, the story changes. In NO case also, whenever a electrophile, let's say, attacks on ortho and para positions, so in this case I'll be showing you a para position attack, So, or attachment will have something like this was the case, and we would have positive charge here and N double bond O here. So lone pair would actually come in resonance to actually stabilize the carbocation, and we would have something like N positive and O. Okay. So as a summary point, let me again retake those examples, the 5th example and the 6th example. So whenever someone comes and asks in the question paper or like that only, we would have, if we have something like this structure, is it activating or deactivating? It is surely deactivating. And this is a, but this is ortho and para-directing. Similarly, don't forget the lone pair to be drawn. Only the lone pair actually changes the game, in which it would have been meta-directing, as we were convinced that it would be meta-directing in my previous examples, but now they are not. And same can be said for this. This is actually a deactivating group, but this is also ortho and para-directing. Okay, now let's move on to another example. You would have something like this. Now we can see that this is a minus I group. Obviously this is also a deactivating group, as it is taking the electron density away from the phenyl ring and given to itself, so it is deactivating group. And this is, but this is ortho and para-directing. How? When it was alone, just with the phenyl ring, minus I effect was dominant effect here. But as soon as the electrophile attaches, or let's say ortho position or meta position, what actually happens here is it also has lone pairs, and that 2-3-3. What will happen is it will donate one of the lone pairs to stabilize the carbonium ion, and it will take positively charged here, and we would have something like this. Okay, in this case, plus M effect of the lone pairs on chlorine atom were more prominent than minus I effect of the chlorine atom itself. But in the above case, when only phenyl ring was considered, minus I effect was considered more dominant than plus M effect. Only according to the situation, these groups tend to change their game and change their colors. Okay, by colors I don't mean the physical color, I mean in a different way. Okay, they actually change their nature as soon as electrophile attaches itself to the phenyl ring. Okay, so with this we come to an end of this lecture. In the next lecture we will be seeing some more examples and the positions in which the electrophile is likely to be attached onto the phenyl ring. So with this, good luck and goodbye.